So let's go back here and look at an example of a flow net that we drew just to sort of refresh our memory on what a flow net is. And the idea of a flow net is that we have two sets of curves, head contours, which are contours of the same head value, and then streamlines are the other set of curves. And these two sets of curves for homogeneous and isotropic systems intersect at right angles, and they make curvilinear squares. So we're going to draw the curves such that we basically have, as close as we can get it, squares in between the head contours and the stream tubes or streamlines. Okay, so this is the basic configuration of the flow net. We talked about some rules for their construction in the case that it's a homogeneous and isotropic system. Streamlines and head contours intersect at right angles. All right, so everything here is at right angles. Head contours intersect no flow boundaries at right angles, which is basically saying that a no flow boundary means no flow in the direction across the boundary, but along the boundary, it's actually a flow line. So flow is occurring along a no flow boundary, but no flow occurs across it. And then we sort of make these sets of curves such that we have these curvilinear squares. So let's now go into some analysis and think about how we can use these flow nets, especially for homogeneous isotropic aquifers, to make some quantitative calculations on the groundwater flow system. So I'm going to draw, so first of all, let's make some assumptions. So we'll start off by assuming that we've got a homogeneous isotropic constant thickness aquifer. And let's go back to our, our simplest drawing where we had this really just a straight system, like for example, the Hellgate Canyon. So as best as I can, I'm going to draw sort of two no flow boundaries here on the sides of our aquifer. And we have flow. Here is our first head contour, H1. Here is our last contour, H2. And H1 is greater than H2, so flow is going in this direction. And now I'm just going to try and divide this thing up evenly. And make these squares as best I can. Okay, so this is my basic Flownet. What I want to do here is I'm going to try and add the third dimension. So I'm going to try and draw the dimension sort of in and out of the screen here. And this is the thickness of our aquifer. So this would be B, this distance here. This is the thickness of my aquifer. And if we now look into this dimension, we've got a series of what we call flow tubes. All right, so this area here, bounded between two streamlines. So remember, this is a streamline or a flow line. The region bounded between two streamlines is a stream tube. All right, so it's this region here. This stream tube is bounded by these two streamlines. And we're going to give streamlines the symbol of let's do phi. In previous years, I've used the symbol psi, but that's really confusing because we're going to use psi for pressure head. So I'm gonna call it phi this year. All right, so I've got two streamlines, phi. And a stream tube between them. Okay, so let's focus in. I'm going to draw just one of these stream tubes. So for example, this stream tube, we're going to isolate it and draw just it. So let's take this stream tube and focus in on it. So here's our stream tube, and our stream tube ends up being this region of our aquifer bounded by two streamlines. And it's got these head contours. I'll just sort of erase this so that it has clean edges. And it's got this dimension here in and out of the screen. And remember that this dimension is B, which is the thickness of our aquifer. Okay, so these are our head contours, and this is our stream tube. Now let's put some dimensions on this. Let's say that this is the X direction. This is the Y direction. And let's put some dimensions on one of these boxes. So let's call this dimension, which is the distance, okay? The distance between head contours, I'm going to call delta X. All right. The distance here between stream lines, let's call this delta Y. Actually, I'm gonna change that. Let's call this delta phi. All right, that's just that's the distance in the Y direction here between two streamlines. We could call it delta Y or delta phi, whatever we want. Now this one is going to be the mind bender. And so let's ask questions and make sure we're clear on what this next dimension I'm about to talk about here. But this is the difference in head between, let's call this contour H1, and this contour is the head H2. Then the difference in head between these two contours is delta H. All right. And even though I draw this line like delta H, in fact, I'm going to try and change my notation because this is confusing every year. I'm going to say the difference between this one and this one is delta H. All right, so that is the head drop between this contour. Let's say this contour has, just arbitrarily picking a number, a head equal to 10. This one has a head equal to 9. Then the delta H here would be equal to 1 meter. 10 minus 9, that'd be 1 meter. All right, so are we clear? Does everybody understand? Delta X here is the distance between the head contours, and delta H is the difference in the head between those two contours. Make sense? All right, not hearing any questions. I'm going to continue on as if we, as if this makes sense. So let's write our first and most important rule for a stream tube. Discharge is constant in a stream tube. So this is super important. super important rule for us when we look at these stream tubes. What does that mean? That means that the flow coming in, say Q in, coming into the stream tube equals the flow going out. And any place I slice this stream tube, the discharge will be the same across in this stream tube. So we can think of a stream tube as a zone, these two flow lines bound an area where the discharge within the aquifer is constant in between those two stream lines. All right, so let's calculate, let's try and calculate the flow in this stream tube here. So let's calculate Q sub S, which is equal to the discharge in, or the discharge out, or the discharge anywhere in this stream tube. All right, Q sub S. So what is Darcy's law for big Q?
Q equals negative K times the area times dH over dL.
All right, Darcy's law for big Q. So now let's write this for the stream tube. And thank you, Finch, for answering. I was wondering how long I was going to have to wait. Okay. Negative K. This is my area here. So what is my area of this face?
Would it be B times delta phi?
Yeah, perfect, Autumn, thanks. So B times delta phi, right? That's this leg times this leg. So B times delta phi. That delta is horrible. Looks like an A. Okay. Now, what can we put in here for DH? The change in head.
Delta H?
Yeah, delta H, just the change in head between these two contours. So let's put delta H in here. And now what is the difference in the X direction over that delta H? This DL.
Delta X.
Delta X. Great. All right. So here's Darcy's law for our stream tube. Now, if we drew this right for this homogeneous and isotropic media, then these are squares, right? And so delta X is equal to delta phi. So these two cancel out. And I get this. The discharge of my stream tube is equal to negative K times delta H. Negative K times B times delta H. All right. So delta H is my contour interval. K is my hydraulic conductivity, and B is the thickness of my aquifer. I'm going to introduce an important quantity right now. T, which we call the transmissivity of the aquifer. We're going to define that as the hydraulic conductivity times the thickness. All right. That is a very characteristic quantity for an aquifer. It's the hydraulic conductivity of the material the aquifer is made of times the thickness of the aquifer, transmissivity. And you'll hear that used a lot in hydrogeology studies or written up in hydrogeologic papers. Transmissivity is equal to the conductivity times the thickness. So using the definition of transmissivity, we can write the stream tube discharge Q sub S is equal to T negative T times delta H. And remember, this negative sign is just to make sure that we're moving in the right direction. Whether or not we really want to include it, you know, it's just so that we know we're moving in the right direction. All right, so the discharge from a stream tube, negative T times delta H. All right, so this is an important equation. This gives us the discharge from a single stream tube. Now, what do you think? How could I calculate the discharge through this entire aquifer? If I've calculated it through one stream tube, how could I calculate it through my entire flow net? Any ideas?
Could you just multiply the value you get for one stream tube by the number of stream tubes that there are?
Exactly. And that's a key result. Again, this is only for a homogeneous and isotropic unit. But in that case, the discharge through the entire flow net is just the discharge through one stream tube multiplied by the number of stream tubes. So for a homogeneous and isotropic flow net, each stream tube will have the same discharge. So the discharge through the flow net let's call this QT. QT is equal to the number of stream tubes, NS, times the discharge through a stream tube. So equals to negative NS, the number of stream tubes, times the transmissivity of our aquifer, times the head contour interval. Okay, one more slight modification to this equation. This equation works, but it requires that we know the contour interval, which we can always calculate. But sometimes we may not explicitly know the contour interval. And so we can do one more trick here. So how do I, in this flow net up here, how would you calculate what the contour interval is here? You know the value H1 and you know the value H2. How would you calculate what the contour interval here is?
Would you calculate the difference between H1 and H2 and then divide it by how many contours there are?
Yeah, exactly. So here we would say, oh, if I want to figure out how many head, what my contour interval is, I figure out what the head is at the starting, what the head is at the end, and I divide it by the number of contours. The way that you count this is important. So this first contour, it's 0 based. So this first contour is 0. This is 1, 2, 3, 4, 5, 6. So the number of contour intervals here would be 6. So it's 0 based. Start off at 0 and count, and you'll be all right. All right. So to calculate the contour interval, we would do delta H, which is equal to H1 minus H2 over the number of head drops or head contours over NH, the number of contours starting at 0. So this one would be 0, 1, 2, 3, 4, 5, 6. All right, so now capital H here is the difference between my starting and ending head in my Flownet. So I can make one last substitution and substitute this relationship. The delta H, the contour interval, is equal to the total head drop across my Flownet divided by the number of contours, head contours in my Flownet. I'm going to substitute this relationship in here in for delta H into this equation, and I will get this. The total discharge out of my Flownet is equal to the number of stream tubes divided by the number of head contours times the transmissivity of my aquifer times the total head drop in my Flownet. Okay, so this allows me for some pretty complicated geometries. I can have, curvilinear flow nets. I can have, you'll draw in your homework a flow net underneath a dam, and you have stream tubes of a bunch of different lengths and widths but if it's a homogeneous isotropic system, we can calculate the total discharge through our aquifer as the number of stream tubes divided by the number of head drops times the transmissivity of our aquifer. And all we need to know is the total head drop from the starting of our flow path to the end of our flow path. So this is a really important equation for calculating total discharge through groundwater flow systems. All we have to do is draw this flow net. It's a pain, but we can now calculate the total discharge for pretty complex geometries. Okay. Let's go another step in our analysis of stream tubes, and we're gonna just briefly talk about what we call stream function theory. Again, we'll assume homogeneous, isotropic, constant thickness. Aquifer. And again, let's have a, I'm going to draw a stream tube here. And we'll do it in this plane. So here's the X, here's the Y. But now I'm going to think about a stream tube that changes in size. So I'll draw some head contours that are sort of roughly squares. Here. And this, you know, just so that we remember, this does have some sort of cross section in and out of the board, right? So this is a stream tube. Okay. This might be a recall, or it might be the first time you've seen this, but the discharge Q is equal to the fluid velocity times the area, the cross-sectional area. So for example, let's call this Q1. Q1 here would be the fluid velocity at this point, V1, times the cross-sectional area, A1. All right. So this is our fundamental one fundamental equation in hydrology is that the discharge is equal to the fluid velocity times the cross-sectional area. All right. And we also know that our discharge in this stream tube is equal at any point in the stream tube. So this discharge here at the outlet is equal, let's say that maybe this discharge here at this point is Q2, right? Well, we know that the discharge Q1 is equal to the discharge Q2, and that's equal to the velocity, the fluid velocity here at this point, V2, times the cross-sectional area here, A2. So at any point along this tube, the discharge remains constant, and and we come up with this relationship between the area and the velocity. So let's remember that this has this dimension B in and out of the board, which is the sort of thickness of our aquifer. And then the other unit here that defines our cross-sectional area is delta phi, which is the distance between my two stream tubes. So the area here would be V1. The area is delta phi times B. We've already sort of figured that out. Delta phi times B1. And this is the area here at this point. And this has to be equal to V2 times delta phi 2 times B2. And again, we assumed here that it's constant thickness. So B1 is equal to B2, and these two would cancel out. And we get this relationship. B1 delta phi 1 is equal to V2 delta phi 2. All right, so there's an important sort of thing for us to realize here, and that is as the stream tubes get closer together, the velocity must increase. So because these are equal, if delta phi 2 is here, it would be larger. So as delta phi gets larger, then our velocity has to go down. And conversely, we could say as delta phi gets smaller, all right, as the distance between the stream tubes gets smaller, then our velocity must be increasing. All right, so we can look at these flow nets and we can start to conceptualize, oh, the flow paths are getting closer together here. I know my stream or my groundwater velocity must be increasing in this point. Oh, my flow paths are diverging. Groundwater velocity must be decreasing here if we have a homogeneous media. And this another relationship that we can derive here is that as our stream tubes get smaller here, then the spacing between our head contours get smaller, right? So as the stream tube gets closer together, the head gradient increases. So another thing we can see here is that the change in the stream tube distance, so d phi dy, so this change, the change in the difference between the stream tubes is in opposite sign, but basically equal to the change in the head gradient. Because we're homogeneous and isotropic, and because we have to maintain these squares, if I decrease the distance between my streamlines, then I have to decrease the distance between my headlines, and that is essentially increasing the head gradient. All right, so if I decrease this gradient, then I have to increase this gradient.
And for the squares, whenever we have curved stream lines like this, do we just get the closest we can to a square?
Yeah, absolutely. The closest we can get to the square, and it's hard, and so like this one, you know, the way you do it, this curvilinear square thing is to like try and draw a circle in there and make it so that, you know, you can't make this a square, but the idea is that when you draw a curvilinear square, that means this circle, it means that this distance and this distance are the same in the center of this stream tube, right? And that's essentially makes this relationship hold. But this is, yeah, when it's curved, that's what you're doing. And you know, it's really hard. Like this one is not a perfect curvilinear square. And that's just the way it is. It's never going to be perfect. And again, when I look at your flow nets, I am not going to be like, oh, that's not a perfect square. If you drew something like this, right, that's not even close to a square. So you want to make it, you know, close-ish to a square. Okay. Oh dear. Let me. I'm gonna have to quit OneNote and reopen it. Okay. So take this relationship one step further. We can say for a homogeneous media, our Darcy flux is equal to negative K dH dx. And we could also then say this is equal to K d psi, oh, sorry, d phi dy. So we can calculate the flux either from the head gradient or from the stream tube gradient, which is the difference, which is the change in the stream tube width. We're not ever going to calculate it this way, but it gives us some intuition. So essentially, very analogous to this relationship that we wrote up here. The higher, the more closely spaced, stream tube, implies higher flux, right? And the opposite holds. The farther apart my stream tubes are spaced, the lower the flux. So more closely spaced stream tubes means higher flux and higher head gradient. Okay. A couple rules for now. Let's consider what happens for heterogeneous and so let's just call this non-homogeneous and isotropic flow nets. So anytime we don't have isotropy or we don't have homogeneity or even constant thickness, each one of those changes some of the fundamental rules or relationships with our flow nets. There's still one fundamental rule that always holds. The discharge is always constant along a stream tube. So discharge is always constant within a stream tube. Okay, so this relationship V times V1 equals the delta phi times V2 still holds. But V1 and V2, let's write them out in terms of Darcy's law. So does anybody remember how we calculate the fluid velocity from Darcy's law? Maybe let's do this in a slightly smaller step. What is the relationship between groundwater flux and fluid velocity? Anybody? The flux divided by the porosity is equal to the velocity. Anybody remember that? So here I could write V1 is equal to Q over N, which is equal to negative K delta H over delta X divided by N. So I can insert this here, and I get negative K over N, and this is the hydraulic conductivity at our point 1 times delta H1 over delta X1. And this is equal to delta phi to negative K2 over N times delta H1, or sorry, H2 over delta X2. And we can cancel out a few things. We could cancel out these minus signs, and we could cancel out the porosity. So a couple things. The discharge constant remains the same, but now it's no longer a direct correlation between the spacing and the fluid velocity, because we now have these different head gradients modulated by the hydraulic conductivity. So let me just write this out more cleanly. Delta phi 1, K1, delta H1 over delta X1, delta phi 2, K2, delta H2 over delta X2. And now, so now we've got three things that vary. We have this one, our stream tubes, distances can vary. And then our hydraulic conductivity can vary in space, all right? And our head gradient can vary in space, all right? So these three things vary, and the direct correlation between delta phi and delta x, you know, these being always squares doesn't hold. So we no longer have squares in a heterogeneous media. We don't expect them to be squares. We can use these relationships to draw some basic inferences. So for heterogeneous media, it's really hard to sort of draw there's no way to draw a perfect flow net. But there are some things that we can infer from heterogeneous flow nets. So some basic principles that we can derive from this you know set of relationships up here. Because the discharge remains constant. So one is we no longer have squares. We already wrote that. We no longer expect squares. All right. As our hydraulic conductivity goes up, then our gradient goes down. All right, so if our discharge within a tube is remaining constant, all right, if we see the stream tubes come together, well, let me just say this. If our discharge within a stream tube remains constant and we have constant spacing stream tubes, then we have to increase the head gradient in order to maintain the same discharge if our hydraulic conductivity goes down. So if we sort of keep this one constant, the spacing constant, if this goes down, then this one has to go up, or vice versa. If this one goes up, then this one has to go down, if we sort of keep these two constant. If if we say that our head gradient is going to remain constant, then if we keep the third term here constant, then if we move from, let's say, a lower to a higher conductivity, then our spacing between the stream tubes must get smaller. So in general, flow paths converge to high K zones and delta phi goes down when hydraulic conductivity goes up. All right, and for all of these rules, the opposite holds. So delta phi gets bigger if K gets smaller. All right, so these are sort of corollaries here, but a really important rule is if you've got a zone of high hydraulic conductivity, flow paths will converge to that high hydraulic conductivity zone. We've already written this one that, head drop will decrease in hydraulic conductivity. And then the opposite of this is that if my hydraulic conductivity decreases, then my head gradient has to increase. All right. So flow paths converge to high K zones. The corollary to this is flow paths diverge in low perm zones, in low conductivity zones. All right, so basically if we're in heterogeneous media, we no longer expect squares, and we can now look at what the stream tubes and the head gradient are doing to get some inference of whether we're in a high hydraulic conductivity zone or a low hydraulic conductivity zone. So if we see flow paths getting more narrow and the head gradient getting increasing, we know we're hitting a high hydraulic conductivity zone. If we see our flow paths diverging, getting farther apart, and our head gradient really increasing, we know we're hitting a low permeability zone. Okay, I want to make sure one last thing. Isotropy is even more complicated, and we're not really gonna deal with it a lot here, but basically in anisotropy, the hydraulic conductivity has these directional properties, and we no longer expect squares. Again, all right, same as heterogeneity. And in principle, there's no real way to determine, if you have anisotropic and heterogeneous, both of these processes are essentially doing the same thing. And it's almost impossible to sort of, from a Flownet, deal with both of these things at once. But the basic idea is that in an anisotropic media, we can think about this. We've got two stream tubes, and here's our head contours. All right, so this is just one square of our Flownet. And, this is a curvilinear square for a homogeneous media. And that says the radius in these two directions are set by Kx and Ky. So this would be a isotropic media. In a anisotropic media, what we expect is an oval. All right, an ellipse, and the two radii now, again, are set by Kx and ky. And it's actually the relationship here, this distance here is given by 1 over the square root of kx, and this distance is given by 1 over the square root of ky. So as my hydraulic conductivity gets larger, all right, it doesn't make a lot of sense to me. As my no, I'm dividing by a bigger number. As this gets bigger, this should become smaller. I'm not positive on this relationship. I think I must have this backwards somehow. It's what I have in my notes, but it's not making a ton of sense to me. So bottom line is we're not gonna do a lot of anisotropic flow lines or flow nets. But what I do want you guys to know is that you no longer expect squares, and that the difference in these ellipses is set by the ratio of these hydraulic conductivities in the different directions. I need to think a little more about these two relationships and go back through my notes. This is what I have written down in my notes, but I'm not positive this is correct. So let's revisit that maybe a little later, but it's not a huge, it's details. It's not, the main thing is that, again, we no longer expect squares, and that we expect these ovals dependent upon the directional dependence of our hydraulic conductivity. Okay. That pretty much covers our Flownet analysis. And so for the rest of class, well, at least for the next half an hour, I want to start working on these this Stream 2 lab. So I'm going to